So the next section in chapter 13 is all about solids. So we looked at liquids in detail. The whole chapter 14 is on gases. And so we're now starting to talk about solids. And there are two major categories for solids. The first one is what we're going to talk about here, which are crystalline solids. The other type of solid is on page 15, and now those are called amorphous solids. So we'll talk about those amorphous solids later. So what is a crystalline solid? This is by far, most compounds are crystalline solids. It is a solid whose internal arrangement of particles possesses a regular repeating pattern. So a solid whose internal arrangement of particles. And the word particles is important because sometimes they're atoms, sometimes they're ions, sometimes they're molecules. So it's when the internal arrangement of particles possesses a regular repeating pattern. A regular repeating pattern. And the example to the right is of what we would call the unit cell of salt, NaCl. And what the unit cell is the smallest portion of a crystal that represents the structure of the entire crystal when repeated. So it's sort of like the basis. And then if you think of an actual, crystal of salt that you might see, if you're, eating French fries, that it's this pattern right here, this unit cell pattern that's repeated, honestly, billions and billions of times. So a unit cell is the smallest portion of a crystal that reproduces the structure of the entire crystal when repeated. And there are many different types of unit cells that if you take a chemistry course in college, you would have to learn all the different types of them. But for right now, we just call it a unit cell, and that is the smallest pattern. So if we think of, we have solids, and then there are crystalline solids and amorphous solids. There are different types of crystalline solids. And so the different types of crystalline solids are down here. They are categorized by basically what are the particles. Remember, we said a crystalline solid is one who the internal arrangement of the particles. So now, what exactly are the particles? In something called a molecular solid, the particles are molecules. Okay, in an ionic solid, the particles are ions. And in a metallic solid, you guessed it, the particles are metals. Now, the other piece of this is just as a review. We've talked about this earlier. What is actually holding those particles together? In a molecular solid, the particles are molecules. So what is holding those particles together are intermolecular forces. So I'm just going to write held by intermolecular forces, right? And we know there's three types of intermolecular forces. Right, so depending upon whether the intermolecular force is fairly strong, like hydrogen bonding, or pretty weak, like London dispersion forces, that could tell us the strength of the particles in the solid. But in ionic solids, what are they held by? Ionic bonds. Very strong. In metallic solids, what are they held by? Metallic bonds. And this bonding part is really important because bonds are very hard to break. You need to add a lot of energy, which means adding a lot of heat, in order to overcome ionic bonds or metallic bonds. But when you melt a molecular solid, all you need to do is overcome those intermolecular forces, which are generally very weak. There is sort of one exception or another category of a crystalline solid that isn't molecular, ionic, or metallic, and those are covalent network solids. And we've already talked about covalent network solids before when we discussed that covalent compounds generally have low melting points. Covalent network solids were the example of this. These are solids in which the units that make up the three-dimensional network are joined by, you guessed it, covalent bonds. So solids in which the units that make up the three-dimensional network, right? That's why it's called a network solid. Are joined by covalent bonds. And now bonds, covalent, ionic, metallic, are always very strong when compared with intermolecular forces. And there aren't too many examples of this, but a great example is that of a diamond. So diamond, all of these are what we would call allotropes of carbon. An allotrope are two forms of the same pure element. So all of these, if I said, bring me pure carbon, and you brought me a diamond or graphite, which we know is what's in the tip of a pencil, or this is in a kind of exotic molecule called a fullerene that is used in some types of medical research, or carbon nanotubes are kind of related to fullerenes. It's like something that you would study if you were taking a course in materials science. So learning about, like, you know, what can we make a car out of that would make it strong but light, things like that. So diamond, we know all of these black circles are representing carbon atoms, and the white lines are all representing covalent bonds. So if I look at that center carbon atom, it is bonded to 4 other carbon atoms, and then take another carbon atom and it's going to be bonded. And so you get this network where everything is bonded. And then in order to break up that network, you need to add an extreme amount of energy. So to melt a diamond, you need to raise its temperature incredibly high. Same thing sort of with graphite. Graphite, you can see these rings of 6 carbon atoms all held together with covalent bonds, and that goes on forever and ever and ever. But what's a little different with graphite is that these sort of sheets of carbon atoms are layered on top of each other. Kind of think of like a stack of pancakes, right? And what is holding each sheet on top of each other are just intermolecular forces. In fact, because this is non-polar, we would say it's London dispersion forces, which we know are quite weak. And think about the properties that we know about graphite, the tip of a pencil, or what pencil lead, we shouldn't call it that, but what pencil lead is made out of. And it's so soft that you can just drag it across a piece of paper. And literally what happens is layer by layer, yes, I know, layer by layer of the graphite comes off. That's how a pencil works. This table right here just sums up the different types of solids and then their properties. I didn't really talk about atomic solids because there's only helium, argon, krypton, neon. It's just the noble gases. These guys really, they have They work on the same principle because what is holding it together are just intermolecular forces. Okay, so that's what's holding those guys together. And because what's holding them together are fairly weak intermolecular forces, you get the characteristics of soft, low melting points, like close to absolute zero, we mean. This is a great review. Poor conductivity. Because what do you need in order to conduct electricity? You need, what do you need? Charged particles that are free to move. I forgot about that for a second. Yes, and we know that if they're made of molecules, there are no charged particles there. Now, a covalent network solid, right? All three of these, we can put, these are all non-metals. These would be made up of non-metals. But what's different about a covalent network solid is they're connected by covalent bonds, not intermolecular forces. So very hard and very high melting, but still poor conductivity. Because, again, no charged particles, they're not free to move. Okay. When we move to ionic solids, what is holding them together? Ionic bonds. Bonds are much stronger, so there we get high melting points. Poor conductivity because we're talking about the solid. We know that these guys can conduct electricity if they are dissolved in water. But metallic solids are held together by metallic bonds, right? And this, the strength of a metallic bond is very varied, if that makes any sense. So that's why we get soft to hard, low to high. It really depends. But because of this electron C in all metal solids, all metals will conduct electricity. So this is all about crystalline solids. Remember, there was another type of solids that we discussed at the beginning, and those are amorphous solids. So basically, if you know the definition of a crystalline solid, it is the opposite of a crystalline solid. So a solid whose molecular arrangement lacks the regular long-range pattern of a crystal. So a solid whose molecular arrangement lacks, so they don't have it, the regular repeating pattern of a crystal. So basically, not a crystalline solid. And this is really interesting because we look at these two examples here. They're both silicon dioxide. But silicon dioxide has two different forms. You can have crystalline silicon dioxide, which is quartz. It almost looks like glass. It's very strong because it has this regular repeating pattern. But amorphous silicon dioxide, well, that's glass. And if you look at what's going on here, so the silicon dioxide, that would basically be like the silicon is the red and the oxygens are blue. I know it seems a little weird there. But if you look at how these guys are arranged, right? Sometimes you have, like, look at this ring. This is a big ring. And sometimes you have little rings here. Because they have a varied structure, amorphous solids tend to melt over a wide range. That's really weird that they melt over a wide range. What does that mean? Well, what temperature does water melt at? 0 degrees Celsius, right? Or ice melt at, I guess I should say, or water freeze. 0 degrees Celsius. And negative 0.5, it doesn't melt. But as soon as we reach that, we have enough energy to overcome all of the hydrogen bonds because they're all the same distance apart from each other. They're all the same strength. But in an amorphous solid, right, the further apart the particles are, the weaker the intermolecular force. So you can, when you heat up glass, it's going to start melting at one temperature, And then it's going to be sort of in between. It's a very viscous liquid for a long time. And if you've ever seen like glass blowing, maybe next year, if you go on the Italy trip, you will definitely go and see a glass blowing demonstration. And you may have seen one. There's a glass factory in Sandwich on the Cape that does glass blowing demonstrations. And the reason why we're able to do that is because glass is an amorphous solid. It melts over a wide range. So you can manipulate glass when it's sort of in that in-between phase. Think about ice and water. There's no in-between phase with ice and water. It's a solid or a liquid, and that's it. So here are just a summary of, if we're talking about the same temperature, right, these would obviously be, right, just as a reminder that at the same temperature, right, particles can be a gas, a liquid, or a solid. It's all about their intermolecular forces. Right? All of these have the same intermolecular forces, London dispersion forces, because they're all, right? That idea of a molecular solid, it's London dispersion forces. So what makes the difference here? We discussed this in a few, last week actually, in one of the videos from last week. Oh, and actually, just a few in the previous video, that the greater the number of electrons, the more polarizable a molecule will be, and the stronger London dispersion forces, right? So if we're talking London dispersion forces compared with the other ones are generally weak, but because chlorine is, only has atomic number of 17, Cl2 would only have, 34 electrons. These would be comparative, weak London dispersion forces, medium London dispersion forces, and stronger London dispersion forces, which is what gives it the different properties of solid and liquid and gas at the same temperature. Okay, your homework from this section is not much. It is 23 through 26. Again, there's not a lot of problems here. It's just, multiple choice, trying to see if you understand these. And we only have one more video after this. So we'll begin next week with a video on the changes of state. And that will wrap up the notes packet for chapter 13.